So let's say we were trying to think of how many ways we can arrange the three letters A, B, C into different categories. How would you do this? I want you to justify your answer after you thought about it for a minute. Now, what some people are able to do in their minds is to scramble these and put them into several different combinations and then count the number of ways that these could be arranged. So they simply took turns of making the A the first letter, the B the first letter, C the first letter, and some people might have rearranged it starting with making the C the last letter, and then the B the last letter, and the A the last letter. And depending on which ways you would do it, you would get all of the possible combinations, and we can see that there are 1, 2, 3, 4, 5, 6 ultimate ways to do this. And if you didn't do any of the ways that I described, but you still came up to 6 ways, you are also correct. Now, because it was a simple combination and rearrangement, that made it work. But I want you to apply the same methods you did the first time to something that is more complicated like this, right? Toy manufacturer makes a wooden toy in 3 parts. The top part may be colored red, white, or blue. The middle part may be colored orange or black. And the bottom part may be yellow, green, pink, or purple. And we want you to determine how many different colored toys can be produced. Now, if you try to do it the first way that you did the first problem, it might be a little difficult, but I want you to try. Now, if you've given up at this point, that's okay. I think most people would also do the same, because adding 3 layers of complexity from the top, middle, and bottom of the toy, that really changed everything. So when we looked at just the top portion of the toy, you had 3 possibilities, red, white, and blue. But then the middle part allowed 2 possibilities added on to the 3 possibilities that already existed at the top portion of the toy. And so when we added the middle complexity, well, that could have been orange or black. And we had to tie that already to the 2 possibilities, or I should say the 3 possibilities of the top toy. So now, all of a sudden, this changed into 1, 2, 3, 4, 5, 6 possibilities, but that still didn't account for the bottom part of the toy, which of course would have then each broken down into where the bottom of the toy alone presented 4 possibilities. So now we had the top of the toy with 3 possibilities added on to the middle of the toy with 2 possibilities added to those 3 possibilities, and then of course just the bottom of the toy, 4 possibilities added on already to the middle and top possibilities. And so that got complicated quite fast, and when we count each of these up, we ended up with 24 possible ways that you can make this toy, right? Or 24 possible ways of making different colored toys. And so, is there a more set way that we can do this, especially as the scenarios get more complex than just trying to list every single possible one and then counting? Yes, absolutely. And that is called the fundamental counting principle. So what the fundamental counting principle is it's a way to figure out the number of outcomes in a situation with multiple possibilities, kind of like the toy situation we just discussed previously. And the official principle is stated like this, that if there are n1 different objects in a set and n2 different objects in the second set, then the number of different ways of choosing one object from each set, and that's a key word here, in fact I'm going to underline that here, in each set is n1 times n2. Now, I want us to think about that n1 times n2 as a formula that you can abide by, but it doesn't actually necessarily or strictly reserve itself for only 2 events. You can have many events. And so if we're thinking about a strategy in order to solve these problems, the first thing I would do is determine, well, just how many events are there, because that's going to determine how many sets I'm going to multiply by. Then I'm going to determine, once I've got the number of events in total that's going on with whatever situation is described, then I'm going to determine the number of possible ways to do event A and event B, or more if necessary, right? Like we said, it may not just be event A and event B. Then once I figure out the number of events and the number of possible ways that I can actually complete or do all separate events, then I'm going to multiply the events together to create a number of possible solutions. So let's look at a first example here and figure out how that's going to work. So here it says that a new car is available in 3 models, 6 colors, 2 transmissions, and 4 different option packages. How many versions of the car can be created? So the first thing we're going to do is we're going to isolate how many events, or you can think about events as choices that we can make here. Well, for each car, there's going to be a model choice, a color choice, a transmission choice, and an option package choice. So in total, if we add those up here, that's going to be a total of 4 different events or choices. Okay, in some cases, it's more suitable to think about them as choices. Now, each event can be chosen, right? Or each event or each choice has 3 or more or different choices or different amount of choices within it. So if I look at the first choice of models, right, I have 3 choices that come from there. Then if I look at the second choice of colors, then I see that I got 6 color possibilities or choices from there. If I look at the number of transmissions, then I have 2 that are possibilities from here. And then if I look at the option packages, so I'll just write option over here, I can see that there are 4 possibilities or 4 options and choices that I can make. So then when I look at it for the third portion here, and it's, remember, you isolate how many events there are, then you're going to multiply them by each other. So I got event 1 multiplied by event 2 multiplied by event 3 multiplied by event 4. Then what I'm going to do here is my event 1, or the model, can expand into 3. My event 2 in terms of colors can expand into 6. My event 3 in terms of transmission can expand into 2. And the fourth event, the option packages, can expand into 4. And so I got 3 times 6 times 2 times 4, and that gives us a total of 144 versions. Now, if I'm thinking back to the formula, remember when I had said it was n1 times n2? In this case, it'd be n1 times n2 times n3, and actually it should be n4. I don't know why it was written twice over here. Let's change that. And so, again, following the formula and the pathway, we got 144 versions. Let's look at a second example here where it says a math quiz consists of 8 multiple choice questions. Each question has 4 choices, A, B, C, or D. How many different sets of answers are possible? So, how many total choices or events do we have? Well, over here, we can have a possibility of 8 different choices or events. So, for step 1, determining how many events, well, 8. Right? 8 events or choices. I'll just write 8 n's. Right? So n1 to 8. Okay, the second thing is, how many possibilities or how many ways are there to do each event? Well, each choice, so if I think about it, I'm doing these dashes as questions here. I'm going to do 8 possible events. Each question has the possibility of A, B, C, or D. So there are 4 possible ways to do each event. Third, we're going to take each of these events, so n1 times n2 times n3, and we're going to multiply them against each other all the way until we reach the 8th event. Now, since each of these expands into 4 possibilities, we're going to expand it as follows, where each one is 4 times 4 times 4. And then, of course, plugging this into our calculator, we're going to get a rather large number of 65,536 sets of answers that are possible. And I know that seems like a large number, but don't think large numbers are wrong. In fact, it is quite often that when we deal with more complex sets of choices, we get far more possibilities. It's almost exponential. Let's look at another example here before we leave you to do one on your own. For an online banking account, the minimum security standards require a password to have 2 letters followed by 5 digits. The passwords are not case sensitive and no characters are repeated. Okay, that's a key thing here, and I want you to underline anytime something mentions repetition, whether it's not repeated or it says that repetition is allowed. I want you guys to get in the habit of underlining these because that changes everything. How many passwords are possible? Okay, so the first thing we're going to do is we're going to isolate how many events or choices are we allowed to make. Well, you got 2 things going on here. Your password can consist of letters and numbers, so there are ultimately 2 choices or events. Okay, and I'm going to write here letters is one event that you have to choose from, and then the numbers is another event. Okay, the second thing we have to decide is how many different ways are there to do each event. Well, if you think about the alphabet, so one event is the alphabet, so our letters. Well, there are 26 letters in the alphabet. So your first event out of the 2 letter events, okay, because there's 2 ways to do letters here. So that'll have 26 choices. But then the second letter, since no characters can be repeated, then once you've chosen one letter, you only have 25 letters left. So in terms of the letter events, they can one of the events or one of the choices between the 2 choices can be done 26 ways with 26 different letters, and the other one, once that one is chosen, can be done 25. Now, alternatively, we could have also said that there were 7 events. If we go back to step 1, because some people might have approached it this way, and that's totally fine, that there were 7 events, 2 events of which have to be letters, and then the remaining 5 have to be numbers. And that would have worked out the same way anyway. All we did here was, in the original way, we just expanded each of these events or choices as follows. But if you did it like this as 7 events, and you find that's easier to understand, then by all means that works as well. But the same logic flows, where from the first choice or the first event, we had 26 options, which left us only with, since none can be repeated, 25 options left for the second event. The third event, which had to be a number, well, we had 10 numbers to choose from since we can choose digits from 0 to 9. And then once we chose that, then the fourth event, we only had 9 choices left, which then for the fifth event left us only with 8 choices left since we can't repeat. The sixth event left us only with 7 choices, again, since we can't repeat the first 3 numbers that were initially stated. And then the the seventh event, we only had 6 choices left, since, of course, none of these can be repeated. So when I plug in all the possible ways to do each event and I multiply them against each other, again, I get a startling large number, but this is nothing to be worried about because we got quite a complex situation over here of about 19,656,000 passwords that are possible. Okay. And so again, no matter which way you approach it here, you would have got the same answer. Looking back at it now, I would say probably to look at it as 7 events, right? Comprised of 2 letters and 5 numbers is probably the most simplest way to look at it. But if you found the first way simpler, that's fine as well.